Welcome back, everyone. Last time we talked about Transformer, Attention is All You Need, the paper that essentially set the foundation for modern natural language processing. It gave us a deep dive into how attention mechanisms can revolutionize language models. Today, we're continuing that journey by comparing this with an important follow-up. One that moves from the concept of attention into practical applications, generative pre-training and fine-tuning, which has shaped the world of NLP as we know it.
Yeah, I remember we talked about transformers, and they were a big deal because they change how we think about long-term dependencies in language. So, what makes this paper different from that? And why is it so important now?
Great point. This paper builds on the foundation set by transformers and takes it to the next level by introducing generative pre-training. Unlike previous methods that often required vast amounts of labeled data for each new task, this approach leverages unsupervised pre-training, which allows the model to learn general language structures from a massive amount of unlabeled text. This step is then followed by fine-tuning for specific tasks. What's significant is how this method has become a cornerstone of recent AI, leading to models like GPT, ChatGPT, Codex, and even tools like DALE.
That's pretty amazing. So, it's not just about creating good models, but making them versatile and efficient to train for many different tasks, right?
Exactly. The versatility here is key. Recent usage of this method in models like GPT has shown its power across multiple domains, not just in language generation, but also in multimodal applications, programming assistance, and content creation. It's transforming industries by reducing the need for specialized data sets and enabling transfer learning at a scale we hadn't seen before.
And I guess today's paper also talks about why this is such a big leap compared to earlier methods, right?
Absolutely. In today's episode, we'll guide you through how generative pre-training actually works and why it's a game changer. We'll look at the two stages: unsupervised pre-training on massive amounts of data to understand the general structure of language, and then supervised fine-tuning for specific tasks. You'll hear about the benchmarks they've surpassed and why using transformers in this context helps maintain long-term dependencies more effectively than older methods like LSTMs.
Sounds like we're in for a lot of interesting insights. I'm curious to see how they managed to get such big improvements with their approach. Are we diving into the technical details as well?
Indeed, we are. We'll touch on everything from how they pre-train on huge amounts of text to how they cleverly use task-specific input transformations to minimize architectural changes, making the model highly adaptable. We'll also look at the experimental results that show why this is such an effective way to build a language model.
Great! I think having a solid framework that can handle different NLP tasks without needing a completely different model each time could be a real game changer for making AI more accessible.
Precisely. It's all about efficiency and adaptability, which is what makes this approach so exciting. With that said, let's jump right into the first part of the transcript, the abstract, where they lay the foundation for what's to come. Let's explore how generative pre-training sets the stage for effective and versatile language models. Ready?
Let's do it.
All right, so today we're diving into the abstract of this paper, which sets the stage for everything discussed later on. The paper is about improving natural language understanding, basically getting computers to better understand human language, which involves tasks like answering questions, assessing semantic similarities, and classifying documents. Now, the big challenge here is that while there's a ton of unlabeled text available online, there isn't much labeled data for training models on specific tasks. And that makes it hard for models trained on task-specific data to perform well.
I think I get it. There's a lot of text out there that isn't labeled, and labeling data can be a time-consuming and expensive process, right? So, we need a better way to use that data.
Exactly. What the researchers are proposing here is to use generative pre-training of a language model on all that unlabeled text first, which helps the model understand general language patterns. Then, they fine-tune the model for specific tasks like answering questions or detecting semantic similarities. This two-stage process, first learning from a broad, general corpus, and then focusing on a particular task, helps make the model more effective.
That sounds efficient. So, the model learns a general understanding first and then fine-tunes for particular needs. How is this different from previous methods?
Good question. Unlike previous approaches, this one uses task-aware input transformations during the fine-tuning stage. This means they make adjustments to how the model receives the input for each specific task, without needing to change the core architecture of the model itself much. It makes the transfer from general training to specific training smoother and more effective, which is something older methods struggled with. They often required more complex changes to the model to make it work well on new tasks.
Got it. So the model architecture remains pretty much the same, but it's more flexible in how it takes in new types of data. What kind of results did they get with this approach?
They showed that their method significantly outperformed previous task-specific models on a wide range of benchmarks for natural language understanding. They tested their model on 12 different tasks and managed to achieve the best results on 9 of them. For example, they improved common sense reasoning performance by 8.9%, question answering by 5.7%, and textual entailment by 1.5%. These are big jumps in this field.
Wow, those are impressive numbers. It sounds like generative pre-training really gives the model a strong base to build on. Is there anything specific about the model that helped it achieve these results?
Yes, they used a type of model called the transformer, which has a very effective mechanism for handling long-term dependencies in text. Compared to older models like recurrent neural networks, the transformer is much better at keeping track of context over longer stretches, which is crucial for understanding complex language structures. This choice helped them make the model's performance much more consistent across different tasks.
So, transformers are key because they handle long text dependencies better. I think that makes sense now. They're like better organizers of the information, right?
Absolutely, that's a great way to think of it. Transformers organize and retain more useful information across long texts, making them excellent for transfer learning and natural language understanding. The key takeaway from this abstract is that generative pre-training followed by fine-tuning, without extensive architectural changes, provides a powerful and efficient way to enhance language models across various tasks. It's all about learning generally first, and then adapting specifically, and doing it in a way that's resource efficient. Let's move on to the introduction of this paper. Here, they expand on why language understanding is such a big challenge, and how their approach aims to tackle these obstacles. The authors begin by highlighting a key point. Most deep learning methods used in natural language processing, NLP, are highly reliant on large amounts of labeled data. This dependence is a significant bottleneck, because acquiring labeled data is labor-intensive and not always possible.
Right. I remember they mentioned that in the abstract. If models need labeled data for every single task, it's not just slow. It also limits how well the models can be applied to other domains, right?
Exactly. That's a great observation. And it's not just about the quantity of labeled data. Even when there's enough, it's often from a specific domain. For instance, a model trained on movie reviews may not work well for legal documents. So the introduction stresses the need for models that can leverage unlabeled text, since there's so much of it, while also being adaptable to different kinds of specific tasks.
I see. So the aim is to make use of all that rich, in-labeled data more effectively, right?
Yes, precisely. The authors argue that the ability to learn effectively from raw, unlabeled text could be the solution to reduce this heavy dependence on labeled datasets. To do this, they propose combining unsupervised pre-training with supervised fine-tuning. During pre-training, the model learns to predict the next word in a sentence across a broad set of text, which helps it understand the structure and meaning of language in a general sense. Later, it fine-tunes these learned skills to perform specific tasks like answering questions or judging if two sentences are related.
So pre-training is like giving the model general language skills, and fine-tuning is more like preparing it for a specific job. But how exactly does pre-training make the model better at fine-tuning?
That's a great analogy. Think of pre-training as teaching the model the fundamentals of a language, like grammar, syntax, and the relationships between words. It's like giving it a strong foundation to understand language broadly. When the model moves to fine-tuning, it already has this base knowledge, so it's faster and more accurate at understanding the nuances of the specific task. The introduction really emphasizes how this two-stage process is beneficial, because it reduces the amount of task-specific labeled data needed.
That makes a lot of sense. It's like giving it a basic education first, then specializing. But I'm curious, didn't they say other methods also use some form of pre-training? How is this different?
Good point. Yes, other methods did use pre-training, but there are two main differences here. First, previous methods often used pre-trained word embeddings, which only provide word-level information. What the authors are doing here is pre-training entire sentences or paragraphs, which allows the model to capture much deeper relationships beyond just individual words. Second, they use the transformer model for this pre-training, which, as we discussed, is particularly good at managing long-range dependencies. This approach allows for better performance on a variety of tasks without needing major changes in architecture for each new problem.
Got it. So, rather than focusing on just words, they're helping the model learn relationships at a much larger scale, like sentences or even entire paragraphs. And using transformers makes it even more efficient for understanding these bigger contexts.
Exactly. You nailed it. Another thing the introduction talks about is how this approach makes the model not only better, but also more versatile. Because they're not heavily modifying the model for each task, it becomes task agnostic, which means it's capable of adapting to many different kinds of NLP tasks. Whether it's question answering, document classification, or semantic similarity, the same core model can be used effectively across the board.
That seems like a big advantage. Instead of building separate models for everything, you just have one model that can be adapted. It's like a general purpose tool instead of needing a different one for each small job.
Exactly, it's efficient in terms of both time and resources. The introduction really sets up why this is such a valuable approach. It tackles the major limitations of needing labeled data and needing specialized models for every task. And it does so by leveraging unsupervised pre-training in a smart way. By the end of the introduction, you should have a clear idea that their goal is to make models that are both broadly knowledgeable and easily adaptable to specific tasks. And that's the core message of the introduction. They're aiming for versatility and efficiency in natural language understanding by using a broad learning approach first and then focusing it down, all while keeping the architecture straightforward. It's quite an ambitious goal, but the rest of the paper explores how they make it work effectively. Let's move into the related work section. This part shows where their research fits within existing work, comparing their approach to past methods to highlight its uniqueness.
So, what do they say about previous approaches?
They start with semi-supervised learning for NLP, using a small amount of labeled data with a lot of unlabeled data, which helps due to the scarcity of labeled data. Earlier methods used word embeddings, which only captured basic word-level information, lacking the context needed for deeper understanding.
Word embeddings work but are limited, right?
Exactly. More recent methods moved to phrase or sentence-level embeddings, but these still fall short of capturing deeper relationships. The author's method goes further by modeling richer semantics at the paragraph or document level, providing more comprehensive context.
So, they're capturing more than just isolated phrases.
Yes, they also discuss unsupervised pre-training, which isn't new but has mostly been used in other fields like image recognition. Pre-training provides a strong base and prevents overfitting. However, unlike earlier methods that used LSTMs, which struggle with long-range dependencies, the authors use transformers for their ability to capture longer contexts effectively.
Transformers handle long text better, so that's a key advantage.
Absolutely. Another distinction is that earlier models required task-specific architectures or extra features, adding complexity. The authors simplify this with task-specific input transformations, allowing their model to adapt without major architectural changes.
So, their approach is more streamlined.
Exactly. Lastly, they discuss auxiliary training objectives. Previous work used them throughout training to boost performance. The authors mainly rely on effective pre-training and use auxiliary tasks only during fine-tuning, reducing complexity.
So, they need less extra support because of their strong pre-training.
Right. They refine existing concepts, like using transformers for better context, simplifying task adaptations, and reducing dependency on auxiliary tasks to create a more efficient approach. This related work section highlights how their method is less complex and more capable compared to older models. Overall, they've taken what worked before and made it better. More efficient, less complex, and capable of truly understanding the bigger picture in language. All right, now let's get into the framework section. This is where the authors lay out exactly how their approach works. Essentially, the how behind their solution. They break it down into two main stages: unsupervised pre-training and supervised fine-tuning. We've talked a bit about these already, but here they really flesh out the details.
Sounds good. I remember those terms from before: pre-training to learn generally and fine-tuning for the specific task. How do they actually do it in practice?
Great memory. Let's break down each stage. First, there's unsupervised pre-training. The goal here is to learn a representation of language by training on a massive corpus of unlabeled text. Essentially, they use a language modeling objective, which means they train the model to predict the next word in a sequence, given all the words that came before it. By doing this repeatedly over a large amount of text, the model starts to understand the structure, syntax, and even some semantics of language.
So it's like giving the model a huge reading assignment, and its test is to guess the next word every time. That way, it learns how language flows, right?
Exactly. You've got the gist of it, and they use a transformer for this, which, as we've discussed, is really good at understanding context over long stretches of text. This helps the model develop a rich understanding of language patterns, which is incredibly useful when it's time to apply this knowledge to specific tasks.
Right. The transformer can remember what it read a few sentences back, which makes it better at predicting what comes next. So what happens after the pre-training?
After the pre-training, we move to the supervised fine-tuning stage. Here, they take the same model that has been pre-trained and adapt it to specific NLP tasks, like question answering or text classification. For this part, they use labeled datasets, where they know what the correct answers are. The pre-trained model already has a strong understanding of the general structure of language, so fine-tuning is like teaching it the specifics of a particular task.
That makes sense. It's like pre-training gave it a broad education, and fine-tuning is more like job training. Does it need a lot of changes to the model to do the fine-tuning?
Good question. One of the big advantages of their approach is that it doesn't require significant changes to the model architecture during fine-tuning. Instead, they use what they call task-specific input transformations. Essentially, they modify how the input data is formatted for each task, but the core model, the transformer, remains the same. This keeps things simple and avoids the need for building new models from scratch for each task.
Oh, that's clever. So instead of changing the model itself, they just tweak how the input is fed into it. That must save a lot of effort and make the process more efficient, right?
Absolutely. By keeping the changes limited to the input format, they make the whole system much more adaptable. For example, if they're doing text classification, they might just input the text with some added markers to indicate different parts. If they're doing question answering, they concatenate the question and the possible answers in a specific way, allowing the model to learn effectively without a whole new architecture. This flexibility is what makes their approach so powerful.
I see. So it's all about being smart with the input transformations. And that's how they handle different types of tasks with the same underlying model. What about the training objectives? Do they change anything there?
Good observation. During fine-tuning, they do include an interesting twist. They add a language modeling objective as an auxiliary task. So in addition to training the model to perform the specific task, like classifying text or answering a question, they also keep some of that original language modeling going. This helps the model stay well regularized, prevents it from overfitting to the new data, and actually speeds up the learning process.
That's smart. It's like keeping the model's general language skills sharp while it learns the new task, so it doesn't forget everything else it learned in pre-training.
Exactly. That dual objective approach, one for the specific task and one for general language modeling, really strengthens the model's versatility. The authors even mention that this helps the model generalize better, which means it performs well on tasks beyond just the ones it was fine-tuned for.
So they're making sure the model isn't just specialized, but also remains broadly competent in language understanding. It feels like they're really balancing between being specific and being general.
That's a great way to put it. It's all about balance. Getting the best out of both worlds. To wrap up this section, the framework they've created is focused on using minimal changes to achieve maximum adaptability and efficiency. By leveraging the transformer and this two-stage training procedure, they've built a system that learns broadly first and adapts smartly to specifics, all without the need for cumbersome changes. And that's the core idea behind the framework. It's an elegant way to maximize what the model can do while keeping it all streamlined and adaptable. Let's discuss the experiments section. Here, the authors test their model across different natural language understanding tasks, essentially putting their ideas to the test.
So, they used a variety of tasks to show flexibility?
Exactly. They tested on 4 categories: natural language inference, question answering, semantic similarity, and text classification. Each category represents different language skills, like logical reasoning or comprehension.
Each one tests a different skill set. Did they need different input transformations?
Yes, but their input transformation approach was adaptable. For question answering, they combined context, questions, and answers into one sequence. For semantic similarity, they processed sentence pairs in both orders to evaluate similarity.
That's very adaptable. How well did it work?
Impressively well. Across 12 datasets, they achieved state-of-the-art results on 9. For common sense reasoning, story close test, they improved 8.9% over the previous best. On the race dataset, question answering, there was a 5.7% boost and a 1.5% gain for natural language inference, multi-NULI.
Those are big improvements. Did they face any challenges?
Yes, for smaller datasets like RTE, the performance lagged. Their model benefits from more data, which is typical for deep learning.
What about when labeled data was limited?
They relied on pre-training, which gave the model a strong base, and used the auxiliary language modeling objective during fine-tuning to avoid overfitting, especially with scarce data.
Pre-training gave it a solid language base, and the auxiliary task kept it balanced. What's the main takeaway?
Their use of generative pre-training, transformer architecture, and efficient input transformations made the model both effective and versatile. They showed that a task-agnostic model can achieve state-of-the-art performance across many NULP tasks using smart fine-tuning. These experiments prove we're moving toward adaptable models that need less human intervention, capable of understanding and performing well across a wide range of tasks. Moving to the analysis section, this is about understanding why their approach works and which factors impact performance most. It's like taking the model apart to see which elements drive its success.
Like a post-game analysis to figure out why the strategy worked, right? So, where do they start?
Exactly. They begin by examining how much of the model's performance is due to different parts of their setup, starting with the impact of the number of layers transferred from pre-training to fine-tuning.
They wanted to see if using more pre-trained layers made a big difference. What did they find?
They found that the more layers they transferred, the better the model performed. Each additional transformer layer added value, improving accuracy on tasks like multi-NLI and RACE. This suggests each layer learned something unique and useful during pre-training, making the model more capable.
It sounds like each layer builds on the previous one for deeper understanding. Did they analyze anything else?
Yes, they looked at the model's zero-shot behaviors, testing it on tasks it hadn't directly been trained for to see if pre-training taught useful general skills.
So, they tested if it could handle tasks out of the box. How did it do?
Surprisingly well. Over pre-training, the model improved its zero-shot tasks, showing it wasn't just memorizing but acquiring linguistic and reasoning capabilities. It made reasonable guesses in tasks like sentiment analysis and question answering, based purely on pre-training.
It's like the model learned to read between the lines. Why did this work so well?
A major factor was the transformer architecture, which effectively manages long-range dependencies and context, allowing the model to understand relationships across whole documents or conversations.
Amazing how the architecture contributes to flexibility. Did they go deeper into performance?
Yes, through ablation studies, systematically altering parts to see effects. Removing the auxiliary language modeling objective during fine-tuning led to performance drops, especially for complex reasoning, showing its role in helping the model generalize.
So, The auxiliary objective is more important than it seems. Did they test anything else?
Yes, replacing the transformer with an LSTM showed a major performance drop, proving the transformer's strength in maintaining long-range context. Also, skipping pre-training led to a significant accuracy decrease, highlighting the importance of pre-training for all tasks.
Each part, pre-training, the transformer, the auxiliary objective, adds value. Without them, the model's performance drops.
Exactly. Each component pre-training, the transformer, the auxiliary objective, plays a critical role. Their analysis shows the success isn't due to just one thing, but a combination of strategies making the model robust and adaptable. All right, let's wrap things up with the conclusion. In this section, the authors summarize the main achievements of their work and what it all means for the future of natural language understanding. Essentially, they want to show how their method moves the field forward and what kind of opportunities it opens up.
Great. I think I have a pretty good picture now, but it'll be nice to hear how they tie everything together. How do they start?
They start by reiterating their core goal, improving natural language understanding using a single, task-agnostic model. The key here is that instead of creating different models for each task, they wanted to build one model that could do it all. And the way they achieved this was through their approach of generative pre-training, followed by discriminative fine-tuning. This combination allows the model to first learn general language patterns from a vast amount of unlabeled text, and then adapt to specific tasks using a smaller amount of labeled data.
Right. So they set out to make one flexible model instead of many specialized ones. It's like having a Swiss Army knife instead of a bunch of individual tools.
Exactly. That's a perfect analogy. This idea of a versatile, reusable model is a big shift from the older approach of building specialized tools. They emphasize that by using pre-training on a diverse corpus with long stretches of contiguous text, their model gained a deep understanding of language. This understanding, which includes both world knowledge and the ability to handle long-range dependencies, is what made it possible to successfully transfer the model to different tasks.
So, in a way, the model got smarter not just because of the amount of data, but also because of the type of data and the way it learned from it. They used those long, connected pieces of text to teach it more about real language, right?
You've got it. It's not just about how much data you have, but about how you use it. By training on long, connected pieces, they gave the model a much richer context to learn from. The authors also point out that this ability to effectively use unsupervised pre-training to boost performance on discriminative tasks has been a long-standing goal in machine learning. And their results show that significant gains are indeed achievable. This model outperformed state-of-the-art models on 9 out of 12 tasks, which is a pretty big deal.
It really seems like they've proven that unsupervised learning can be powerful enough to bring these big improvements. What do they say about the future? Like, what's next for this kind of approach?
That's an important part of the conclusion. They're hopeful that this framework will inspire further research into unsupervised learning, not only for natural language processing but potentially in other domains as well. The idea is to keep refining and pushing the boundaries of how well models can learn from raw, unlabeled data, which could make AI more broadly accessible. By reducing the dependence on manually labeled datasets, they envision a future where building powerful models becomes less resource-intensive and more inclusive.
That makes sense. If they can keep improving how much a model can learn without needing labeled data, it could make building models easier and faster, and maybe even allow more people to do it without needing huge resources.
Absolutely. That's the dream, to democratize AI, so it's not just big companies that have the resources to create powerful models. They also note that their success with transformers in this setting provides a clear direction for future architectural choices. The combination of attention mechanisms and pre-training seems to be particularly effective, and they hope that other researchers will build on these findings to explore even better models and new applications.
I guess the take-home message is that they're laying the groundwork for more advanced and accessible AI models. Their success isn't just a single win. It's like a stepping stone for everyone else.
Exactly. That's a wonderful way to put it. Their work provides a strong foundation that can be built upon, and they see it as opening the door for further exploration into both improving the model architectures and making AI technology more practical and accessible. The conclusion isn't just about their achievements, it's about setting the stage for what could come next. And that's how they close things out, by emphasizing that their approach has both advanced the state of the art and also shown a clear path forward for the future of AI research. It's exciting to think about all the possibilities that could come from here. And that wraps up our discussion on generative pre-training and fine-tuning for natural language understanding. I think it's safe to say that this approach really set the stage for everything we're seeing in AI today, from versatile language models to multimodal applications. Looking ahead, it's exciting to imagine how refining these methods could lead to even more adaptable and efficient models, potentially reducing the need for labeled data even further.
Absolutely. Maybe we'll even see these models become intuitive enough to tackle brand new types of problems without any specific training. It feels like we're just scratching the surface of what's possible.
Exactly. The future holds so much potential, especially as researchers continue to push the boundaries of what these models can learn and do. We hope today's episode gave you some valuable insights into why generative pre-training is so transformative and where we might be headed next.
Thanks for tuning in, everyone. We hope you enjoyed diving deep into this fascinating topic as much as we did.
Yes, thank you all for listening. If you enjoyed today's discussion, stay with us for the next episode, where we'll explore another groundbreaking advancement in AI research. Until then, keep learning and stay curious.
See you next time.